Good morning, students. Let me get the IPEVO warmed up. I always leave it open, but then it closes automatically. Let me just get this set up for us. Well, I hope everyone's doing okay. The thing about the Thanksgiving break is that it's certainly welcome, but it's like the calm before the storm. Hopefully, you'll have an opportunity to use tomorrow if you need it as a flexible day. I know your break starts, but I asked several students would they appreciate an extra day to get a test done and get some homework done, and then move everything else on to Sunday and next week. And they said yes. And so take advantage of that if that will make some of your time off a little less stressful. I know you have work in other classes because your time is valuable, and a lot of you have obligations, you know, with your families and also with jobs and things like that. So it's a very busy time. Sometimes I wish, as a musician, also I wish that the holiday season were less stressful so I could actually enjoy it more. But I always remind myself if I weren't doing what I love to do, it would be less joyful. So we're grateful for what we have, and I'm glad that everyone continues to have good health. Please be careful. Please be very careful. Now that we've got regular influenza that will hit along with the COVID, it's important to wear your masks and just be very careful. It's just not, when you think about it, you have no idea how the COVID can affect you. Everybody's different, and I don't want any of you to fall ill. I've had a couple of students who have been sick, and fortunately they were okay, but they've had relatives that didn't do as well. So please continue to be careful, and with the vaccine, hopefully we'll be even in better shape as we get into the spring semester, and keep our fingers crossed that things will start to calm down some. So I appreciate your hard work. I'm sure by the end of the term you will be glad to prop up your feet and take a break from mathematics. Now today what we want to do is cover sequences and sums. And like the conic sections, ladies and gentlemen, this material is less difficult than the trigonometry, but it is very important. You will use conic sections in calculus and physics and engineering, and you will definitely use the sequences and the sums in the calculus. So this again will be pre-calculus. I mean, really think about what we do, ladies and gentlemen. Pre-calculus means material before the calculus to get you ready. So let me go ahead and share my screen and we'll get started. And let me move Professor Ron over. I tell you, I've got all these little windows open. So what we want to do is start with the sequence and basically describe that in terms, let me adjust this. I always move things around a little bit. I like it to be just right. And of course, that's the math professor hanging on. So let's see what we got here. So let me move this up down just a little bit. There we go. So to get the ball rolling, let's just write what we're going to be doing today: sequences and sums. And sums are actually going to be partial sums, and they're going to actually be sequences also, and I'll show you that. So to get the ball rolling, let's start with the definition of a real sequence. A real sequence, and of course you can have all kinds of sequences, but this is what we'll focus on in this class and what you'll also do in calculus. A real sequence is a function f whose domain is the counting numbers, the natural numbers, and the range, obviously, the real numbers. So we say a real sequence when we focus on the outputs. And what we can see here is, in this case, this is basically an ordered list. Now, when we say natural numbers, basically 1, 2, 3, ordering the list, so to speak. Now, there'll be occasions, ladies and gentlemen, when we'll start with 0, and that's not to throw a thorn in your side or anything like that. It's just convenient sometimes to do that. But for most of the problems that we have, we'll only get a 0 when we re-index a sum. So in this case, we have a notation that is useful for sequences. And I know you've seen this before. If we write a function, we say like f of 1 would be the input of 1, but instead of writing that, we're going to say a sub 1 or b sub 1 or c sub 1 as a sequence. Now, there's nothing wrong with this, but this has become standard. And so the second term of the sequence is really f of 2, but we'll just label that a sub 2, etc. So f of 3, a sub 3. And so when we get to an nth term, we say the input is n, and the notation for that is a sub n. So again, this is what we call an ordered list. Like when you would do your standardized testing in, say for instance, when you were in high school and you have the standardized testing, a very common question is like an ordered list where you discern a pattern and figure out basically what the next term in the sequence is, or next term in this particular list is. And so this is a common form. That is, for the general term, we will use the notation a sub n. So what I want to do is use some examples and use that as a springboard to the different types of sequences that we'll encounter today. So let's look at an example where we have an ordered list. I'll just list a sequence. Say 1/3, 1/9, 1/27, 1/81, and then 1/243, etc. So this is actually a special case. This sequence is actually geometric. Now, when you look at this, you're thinking, okay, well, it appears that we start with 1/3, and there is a pattern here. When you do your WebAssign problems, the sequences will basically have patterns that you can discern and write some type of general term, but that's not always the case. Sequences can be very random, like a random number generator. Often you can write a sequence of code or lines of code that will produce random numbers. And so that would be really hard to decide. I mean, that's a probability problem. So sequences don't have to be always so well behaved, but the ones we talk about today will be for the most part. So when you look at this, we have 1/3, and then if we multiply 1/3 by 1/3, we get 1/9. And of course, if we multiply 1/3 by 1/9, we get 1/27. Even if we don't even notice that, we can see in this case that this is 1/3 to the first power, 1/3 to the second power, etc. So this would imply, or equivalently, that we could write a general term, a sub n equals 1/3 to the nth power, where we would let n be greater than or equal to 1. So that would be a form of the general term that would definitely describe this particular sequence. And so in just a few minutes, we're going to take this idea of geometric and try to come up with a general term and also a partial sum. Now, one thing about sequences, they're very useful when we study objects called sums, finite sums and infinite sums. So when you study the calculus, you'll study Riemann sums for the Riemann integral. And when you study calculus 2, you'll study infinite sums to understand sequences that converge at infinity. So in order to do that, we need to kind of get our feet wet with what we call a sum or a partial sum. So let's take this idea here and define the nth partial sum. Nth partial sum. And what this is going to be, it's going to be notated with an S and a subscript N. And basically, it's going to be adding the first n terms of a sequence. So if we just called them by this standard notation here, this would just be a sub 1 plus a sub 2 plus a sub 3 to the nth term, a sub n. This is what we would call an nth partial sum. That means we add the first n terms of the sequence. So what you can see here is that this basically is a sequence itself. We could have the first partial sum, the second partial sum, the third partial sum, etc. So we make a sequence from a sequence. Now, what we try to do is incorporate a shorthand notation because of the convenience of sums and that the fact that finite sums are convergent. We want to treat them like algebraic objects, and we want to add them, subtract them, multiply. We want to factor constants, decompose them into several sums if it helps us solve particular problems. So this would be more conveniently written as the following. We can take an index variable of 1, k equal 1 to n, and write a sub k. So the idea is that for each value of k, we get a summand. So when k is equal to 1, we get a sub 1. When k is equal to 2, we get a sub 2, etc. And then, of course, at the upper limit, when k is equal to n, we get a sub n. Now, what does this Greek sigma mean? It means add all of the terms that you generated as you have the varying values of k. So in order to write this finite sum in shorthand, we use the Greek sigma. And again, k is just the index. Now, one reason for switching to k here is that we're already using the n, so we wouldn't want to reuse the n here. That would get a little bit confusing. So we would say, to make it clear, we'd just use k or your favorite letter, I or M, or any letter. These happen to be the most popular. Now, if we look at this particular sum here, this sequence, let's write the formula for the partial sum. So S sub n, so we've got a particular a sub k here, and it's this guy. So we'll write it this way. So we'll have a sub k, which is 1/3 to the k. So this would be a shorthand notation for the partial sum here. Again, switching to the k variable as the index. So let's write down several of these partial sums just to get some practice. Now, we'll say that this particular type of sequence can be investigated further, and we'll do that momentarily. So S1 is just, well, we just have one term. We start at 1 and end with 1. So we have one term, and that's just going to be 1/3. 1/3 to the k, and k is equal to 1, 1/3. And then S2, the second partial sum will just be 1/3 plus the second term that's generated will be 1/9. So we can get 9, and then of course 3. 3 times 1 is 3 plus 1, so we just get 4/9. Let's do a couple more just to get the general idea. Now, of course, here, this will be 1/3 plus 1/9 plus 1/27. Now, we've already added the first two terms, so we can substitute here. This will be 4/9 plus 1/27. So we get a 27. So 9 into the 27 is 3. 3 times the 4, that'll be 12 plus a 1. And this will give us 13 over 27. And you might be thinking, do all partial sums evolve this way? I mean, is it possible to get a formula? And in some cases it is, and we will see that. So S sub 4, again, we'll add the first 4 terms of the sequence here. And this is a nice analysis. Many problems take the form of partial sums. And so understanding this is important. This particular sequence is important, like the Pythagorean theorem. So we will use it heavily. So now the first 3 terms give us 13 over 27 plus 1 over 81. So of course, 27 into 81 is 3. 3 times the 13, that gives us a 39 plus a 1. So this gives us 40 over 81. So the idea of a partial sum basically just means that we take the terms of the sequence and we create a new sequence. Sometimes, ladies and gentlemen, when you refer to a sequence, you just refer to its general term. You say, let's consider the sequence A sub n. Sometimes it's put in curly braces like this, A sub n equals 1 to infinity, but that's too cumbersome. So mainly what we do is we just refer, like we'll say, consider the function f, consider the sequence A sub n, which is a function. So we usually get really lazy and just call it that. Now the sequence of partial sums, we can write it that way, or we could do something like this too. Even though that's a little bit much, usually the context will be clear. We'll just say, consider the sequence of partial sums. So our notation is convenient and easy and usually efficient to write. We like that in mathematics. So let's look at this particular type of sequence and see if we can get some additional details about it. Again, this is probably one of the most important sequences you will use in calculus, aside from the telescoping, which we'll talk about soon. So let's look at this. Now, just like when we were doing the conic sections and we just kind of looked like we made up everything from scratch and didn't set up a convention, we do the same thing with the geometric. So let's just call this the geometric sequence. Some of the problems in the WebAssign are very straightforward and very dry and boring. Just to give you some basic build up, so to speak, just some way to, what's the word I'm looking for? Just to practice, so to speak. So you won't find them very difficult, just reinforcement ideas. But the evolution to the sums and all is what will be the main focus and what I'm interested in. So for instance, we'll have an A and an R that are both non-zero. And additionally, we really don't care for the R to be 1. In that case, multiplying anything by 1, it's the multiplicative identity. So the 1 for the R will not be considered. But any A and R that are non-zero would be permitted. And then the sequence we're going to write this way, and this is the standard notation. We'll say the first term is A, so that's A sub 1, we just call it A. And then the second term we get by multiplying A by R. Now, one usage here is often done this way. That is, we will denote the R by the phrase common ratio. Common ratio. Now, I don't care if you call it common ratio, you can just call it R. We just notice that as we move from one term to the next, from left to right, we have a factor of R. Or if we take the ratio of A over R to A, we get R. That's why they call it the common ratio. And then to get the third term, we'll multiply AR times R to get AR squared. So this is what we think of as the first term, the second term, the third term, and then the fourth term, etc. And then, of course, down to the nth term, that would be ARN minus 1. So we start with A, multiply by R, multiply by R, multiply by R. So that's what we call geometric. Any sequence that has this property is geometric. Now, so now you can see here the general term is just A R to the n minus 1, where n is greater than or equal to 1. So that, again, once you start thinking about what the sequence looks like, you evolve a general term, and this is standard. Again, we will assume that R to the 0 power by definition is 1. So when n is 1, we just get A. And then, of course, when n equals 2, we get A R to the 2 minus 1, which is just AR. So this general term is meeting the needs that we have for this particular sequence. Now, so that was the easy part. So what we want to do is see if we can come up using just some basic properties about finite sums, see if we can come up with a formula for the partial sum, as opposed to just having to add, one term at a time. Is there a quicker way to get to a partial sum? And then would it be possible to actually add an infinite number of these terms and actually get a finite number? And I think what we're going to see is that the answer to that question is yes. So let's look at the partial sum. Just like we did before, we'll use k's. So we have k equal 1 to n, a r k minus 1. Now, what we see here is this looks just like this, but now we have a new index variable k because we're using n as the subscript, adding the first n terms of the geometric sequence. Now, we want to use a little bit of algebra. Now, let's take the partial sum, and what we want to do, this will be our first example of a telescoping sum. What we want to do is multiply the partial sum by the common ratio R. So here's a nice technique that was observed about this particular sequence. So what is S sub n minus R times S sub n? Is that simple? And the answer is yes. Let's see why that is true. First, we're just going to go ahead and factor the S sub n and write that as S sub n times 1 minus R. And now what we want to do is use some properties of sums. So let's write down the formula here, and then of course multiply this by R, which would just change this to a K. That would be R times R to the K minus 1. The 1 and the minus 1 would give us the 0 and just give us R to the K. So now we get, upon multiplication, the first term not changing, S sub n. And then when we do R, again, we multiply by the R. The R can come inside. Has no bearing on the K, no dependence there. So this will just give us minus, just like working with polynomials. K equals 1 to n A R K. So just using the laws of exponents. Now, when we look at this, what's interesting about this is that we're thinking, how do we get all of these terms to go away, Professor Ron? What you're saying that things are going to absorb, so to speak. Well, the way we can see that is just like looking at adding or subtracting like terms. These terms are not the same here. We need an R to the K here and an R to the K here. So in order to make that work, we can replace K with K plus 1. So if we replace K with K plus 1, we get K plus 1 minus 1, which is K. So basically, we're adding 1 to the K. And then, of course, if we make this bigger by 1, we have to make the index variable smaller by 1. So we'd have to start at 0. So that's a simple fix, so to speak, a re-indexing. So we have k equals 0. Now we only ascend to n minus 1 because we're basically here subtracting 1 from the index variables, but then adding 1 to the k here to get just k. So replace k with k minus 1. So the k minus 1 becomes the k, but then to compensate for that, we start now at 0. So now when k is equal to 0, we just get a. When k equals 1, again, we just get a. So these are equivalent. So we've just done a re-indexing, and I wrote it in red here so you can see what we did. Now we have minus k equal 1 to n ARK. Now, if you look at this, if you notice this part here, you're thinking, well, there are a lot of terms here that absorb, but this has a k equals 0 term that this one doesn't have, and this has a k equal n term that this one doesn't have. So what we want to do is just kind of take those away from the sums so we can see the telescoping. So now, let's write down the k equals 0 term, which will just be a. And now we can write the sum without the 0 term and start at 1, n minus 1. So we just basically pulled off the 0 term here. So that's k equals 0. Now over here, we have the n minus 1 term here at the top, but we don't have the n term. So here we want to pull off the n term. So now we'll have minus k equals 1 to n minus 1 ARK. And then, of course, the n term will be just with the minus AR to the n. So this is k equal n. Now you can see that these are the same. I mean, we're adding from 1 to n minus 1, AR to the k. But that's just what this is. This is the opposite. These are equals and opposite. So this is what we call telescoping. It's like, you know, when you're using a telescope to see things, you're bringing things in closer. So what was wide and expansive is now retracted to nothing, so to speak. That's how the term telescoping came about. And so what happens here is that you see pretty much all of the terms absorbed, and the only thing that's left are these extreme terms. So telescoping is a really, really important type of sum. Again, it makes for an easy partial sum, and telescoping, just like geometric, will be very important to us in the calculus. So now what's left? That's 0. So we have a plus, or excuse me, minus. I've got a minus sign over there, so let me remember that. Minus AR to the n. And now, of course, since we factor everything to death, that's just a times 1 minus r to the n. So if we compare the equals, we now have a formula for S sub n. We can just divide by 1 minus r. So equivalently, we have S sub n equals a times 1 minus r to the n divided by 1 minus r. So it's really important that we don't consider r equal 1. That is of no consequence to us. And of course, this wouldn't even make sense if r equals 1. So now we have a partial sum formula. Notice this has no summation in it. This is a closed form, what is it? A closed form representation. A closed form representation of this sum right here. And so we don't have to do any physical summing. We now have shown that this is equivalent to this. And so this is not always the case, ladies and gentlemen. We rarely get this, but when we do, we're very happy. So we just call this the formula for the nth partial sum. So this is a special case, but like the Pythagorean theorem, this is extremely important to us in mathematics. I can't even begin to tell you, it's like, could you imagine trying to do trig without the Pythagorean theorem? It'd a no-go. We'd have to come up with something else, or would we even need it without it? You see, it's just like there's certain linchpins in mathematics that are important. This is one of them. So now let's go back to the example where we were with the 1/3. The first term, remember, was 1/3, and R was also 1/3. That is, we had 1/3, 1/9, 1/27, etc. And we computed S4 the old-fashioned way, but again, you're thinking that still takes computation, exactly. But when n is really large, we still have an exact representation. This is better. The sum is fine, it's exact, but this is better because we can always get a physical number, again, that's a little bit more attractive here. This may be better for our calculations. So we can say S sub 4. So now we have A equals 1/3, R equals 1/3, and N equals 4. So let's see what we get. So we get 1/3, 1 minus 1/3 to the 4th, divided by 1 minus 1/3. So now, of course, we have a 1/3, and then, of course, here, this is a 3 minus a 1, so that's a 2/3. And what do we have inside? Of course, the 3's are going to absorb. So we're going to have a 1 minus 1/81. And so now the 3's absorb, and we have 1/2. And then we can get a common denominator of 81. So that'll be an 81 minus 1 when we repair that. So this is 1/2 times 80/81. And of course, 2 into 80 is 40. So we get the same response, of course, 40 divided by 81. So the nice part about the, I mean, of course, if you've got fancy computers and things, you know, they can add and subtract really fast, but there are often times when we need exact calculations or we need a formula to push our computation forward. And so the geometric is always right at our fingertips. We can always say, okay, I really know what this is in terms of a closed form representation. Now, when you think about this, what about the infinite case? For instance, does this make sense if we were thinking about an infinite sum? So we have S of n equals A times 1 minus R to the n divided by 1 minus R. Okay, well, in calculus, you will actually be able to prove this, but intuitively, it makes plenty of sense. If we assume that R, the common ratio, in absolute value is less than 1, then powers of the R converge to 0 as n passes to infinity. That is, this implies that the limit as n approaches infinity, kind of like what we were doing with our asymptotes in the slant asymptotes for the hyperbola. Remember, we did that and did some nice algebra there. You will be able to prove this by definition. That is, when you take higher and higher powers of a number in absolute value less than 1, the output gets smaller and smaller in the sense that the output converges to 0. That is, this limit is 0. Now again, I'll say you will have your proof in calculus once you have the definition for convergence of a sequence. And so the idea is that if this is true, then we can actually write we can write a formula for S sub infinity. So that would mean that now we can use K or N or whatever. Now we can just use N if you want, because infinity is going to go up here. So we say N equal 1, A R to the N minus 1. We can use any variable we want here, ladies and gentlemen, as long as it's clear and making sure that we're not using it elsewhere in the problem. And so if we look at this, the term here, the R sub n, becomes 0 in the limit, and we're just left with the A divided by 1 minus R. So the infinite sum is very, very simple. There is no R to have to, no N to contend with, and we get a very simple formula, A divided by 1 minus R, which again is used quite often in the calculus and in power series when we talk about intervals of convergence. So you're looking here and saying, wow, that's even simpler than the formula for the partial sum. And so this is true when the common ratio is less than 1 in absolute value. So we would say, when this is true, that this infinite sum actually has a value. And that's when we say converges. Converges. So basically the limit here, that is as n passes to infinity, the limit is an actual real number. Now, when we don't have this, that is if R in absolute value is greater than or equal to 1, we have diverges. So we'd say converges for R in absolute value less than 1, but diverges when we have this. And this will be a result that you use and prove in calculus. We can talk about it now, but that'll be something you'll talk more in depth in when you take calculus 2. This is actually the introduction to it. And we want to make sure that when you see this again, it's not just the first time. So what we see here, ladies and gentlemen, is that this geometric sequence is really, really powerful and really unique to our mathematics. We get a lot of output for what appears to be a minimal input. So we'll use this to do some examples. Now, there's another sequence called the arithmetic, which doesn't have all the nice properties of the geometric. But before we do that, we need to get some other details. So these other details will be famous formulas and also just an awareness of the algebra of the finite sum. So I call these the famous formulas. You use these in calculus. And we'll be able to prove some of these by induction. There are all kinds of ways to prove things, ladies and gentlemen, and one proof is not necessarily better than another. We just want to have some way to substantiate what we have. So let's write down a few famous formulas. Let's take C to be a non-zero constant. So this is, we'll fix this. Fixed. So I'll just write fixed C, like we're doing the A and the C in the conic sections. So for instance, if we just take a number and add it to itself n times, and here I'll use a K since I'm going to say n times. C is just a constant, and it has no dependence on the K. So when K is equal to 1, we get C. When K is equal to 2, we get C. So basically, we add C to itself n times. This is a very useful formula. And it occurs a lot in sums. So again, you can think of factoring the C and just adding 1 to itself n times, and you get C times what? N. So it's the same result. So that's an easy result, but very useful. 2, this famous formula just adds the first n counting number. So let's just say K equals 1 to n of K. And so when we think of this, this is just saying 1 plus 2 plus 3 ascending to n. So again, when we've got a very simple, very, very simple generating sequence, and when we do the partial sums, there's a nice formula for this. So if you add the first n counting numbers, there's actually a closed form representation, n times n plus 1 divided by 2. So what's nice about these is that all you do is pick off the n, say that's a 5 or a 10 or whatever, and then you substitute it in here and you get the actual value from 1 up to that number in sum. So these actually can be generated for all positive integer powers of k. So these formulas are very widely used, but the first three that I'm going to write here, we actually see a lot in calculus, actually all 4 of them. You'll use every one of these in Cal 1 and then more in Cal 1 than you do in Cal 2. Cal 2 will use a lot of the manipulations that we did to prove this in the geometric case. 3, let's do the same for the squares. That is k equals 1 to n of the square of the counting numbers. So now we'll do 1 squared plus 2 squared plus 3 squared, etc., squaring all of these. So this will be 1 squared plus 2 squared, etc., to n squared. This also has a famous formula. It looks like this: n times n plus 1 times 2n plus 1. Now these can be generated algebraically. Actually, I'm going to try to show you some inductive proofs of this when I do mathematical induction with you when you get back. So the idea here is that the induction argument will basically verify these formulas. They don't give you an algebraic proof so much as that they take the formula that you have presented, and it's a verification process. So the inductive principle is extremely important and used widely in discrete math and computer science. Some mathematicians will not accept an algebraic proof when it's about natural numbers. They have to see an inductive proof. I'm flexible. I think either way is fine. But there's some mathematicians that always have to see this regardless of how it worked out. But that's just a matter of taste. Now the very last one will be summing the cubes. K equal 1 to n of k cubed. So we'd have 1 cubed, 2 cubed of the n cubed. Well, this formula turns out to be the square of this one. N squared times n plus 1 squared over 4. Now the algebraic proofs are a little bit tedious with the manipulations of the sums, but they're doable. And so one nice thing about the computer algorithms of our technological age is that these can easily be generated with algorithmic processes, kind of like your WebAssign generates random numbers to go into your problems and things. It can be very useful to generate things. So we will often be very happy that we have a induction proof to come to our defense when we try to verify these. Now, I want to show you that with formulas like this, you can actually do computations in a straightforward manner using the properties of the sum and these famous formulas. So here's an example. Sometimes the WebAssign will say, we'll use a graphing calculator. You don't want to do that. You want to do it as I have taught you to get the utility of working with the sums. That's the main thing here. I mean, you don't need to know pre-calculus or calculus to use a fancy calculator. You can teach a 4th grader to do that. I mean, that's not going to get you anywhere. It's great to have Google to get a nice calculus approximation, but we really need to understand what's going on here. So let's look at an example. And the nice thing about this, it doesn't matter how large the upper index is. If you're using the famous formulas, you'll always get a nice clean number. So let's look at this. 2k squared plus 5. So when we look at this and we think about summing that is, here's our generating sequence. And so we've got a value at 1, a value at 2, a value at 3, all the way up to 15, which we must add together. So the idea here is that we can actually break this up and use one of our famous formulas or two of them to get a nice answer. So here's what we're going to do first. This is finite, so we can break it up into pieces, or convergent, as they say. So this will be the sum of k equal 1 to 15 of 2k squared plus the sum k equals 1 to 15 of 5. And so now notice here, this 2 has no dependence on the k, so it can be factored. So this will be 2, k equals 1 to 15. And then we have k squared. Now we notice that this just parallels this. This is adding 5 to itself 15 times. So this is plus, if you want to say 15 times 5. So now this is the famous formula right here, and we have the closed form representation of that, where we just replace what, n with 15. So this will give us 2, and we'll have what, 15, and then we'll have 15 plus 1, which is 16. And now we have 2 times 15, that's a 30 plus a 1, so we get 31. All divided by 6. Plus, and now we can still write this as 15 times 5. Maybe we'll be able to factor later. We'll just see how the numbers work out. Now I've noticed here that this is just 2 times 3. So when you look here, the 2 will absorb into this 2, and the 3 will absorb into the 15, giving us a 5. So the 2 and the 5, or 2 and the 3 go away. So this will be 5 times 16 times a 31. That's all that's left there. And then, of course, we have 15, or 5 times 15. And notice now we've got a common factor of 5, which we can extract, and no others. So this will be 5. So we have a 16. Of course, 16 times a 31, we can write as 16 times a 30 plus a 1 to make it easier to multiply, plus 15. So like you're saying, you could just add them all up, but this is a lot less worrisome than that. This is less computation, so it's usually more efficient and less error prone. So now we have 5, and so we have a 3 times a 6. That'll be, in this case, an 18 with a 1, so 480, add the 0, plus 16, plus 15. So now, of course, the 16 plus the 15, that's a 31. So 480 plus 31. Now we can add those. So that'll be a 1. And then we have a 3 plus an 8, that's an 11. And another 1 gives us a 511. So now we can easily multiply this by 5. We get 5 and a 5. And then 5 times 5 gives us the 25. So the sum, the partial sum here is actually 2,555. So the idea here is that we don't really have to recognize any pattern with this sum. Basically, we see that we have formulas that actually do these partial sums for us, namely this one here, which was summing the constant term, just multiplying the constant by n, and then of course the sum of the first n squares. So when it comes to doing just basic manipulation of a sum, we can use algebraic techniques that we use when we work with polynomials. factoring, multiplying, breaking things up, and just like we do when we do basic algebra. So we can treat these as algebraic objects. Notice finite sums always converge. Now, some infinite sums, as we've seen, like this one, converge, but a finite sum is just finite. Okay, so you can always add it and it will always give you a finite number. Regardless of how large it is, it's still finite. So we have the luxury of being able to work very flexibly with sums that converge. And when we have convergent infinite sums, we can do the same kind of manipulation. So that's a bonus when you get to calculus. Now, there is another type of sequence that is not as popular as the telescoping nor the geometric, but it is useful and comes up a lot in computation. It's called the arithmetic or arithmetic sequence. It usually is pronounced arithmetic sequence as a descriptive. Arithmetic, that's interesting. Our language is very, very useful, yet very strange at times. So now what we'll do is we'll assume that we have a non-zero A, just like we had before, as a first term. And now what we're going to do is have a non-zero D. We're not going to care if it equals 1, but we're going to call the D, instead of the common ratio, the common difference. So we need one of our famous formulas to actually compute the partial sum of the arithmetic sequence. And we'll find that that will make our life a lot easier. Now, what's interesting here is that when you think about the arithmetic sequence, it starts out just like the geometric. We call the first term A just by convention. But now to get to the second term, instead of multiplying by D, we add D. So we'll say A plus D. Now, with the geometric, we have another factor of R to get R squared. Now we're going to add another copy of D to get 2D. A plus 2D. So here's our first term, our second term, our third term, and then we'd say A plus 3D for the fourth term. So now, when we ascend to the nth term, we're going to add n minus 1 copies of D to A. So this is very much like the geometric in the way we're setting it up in the convention, very, very similar. So if and only if, so there's our general term here, the nth term will just be the first term plus n minus 1 copies of the common difference, like that. So that indeed is simple. And you're thinking, well, okay, there are arithmetic sequences. You know, you get from one term to the next by adding a common difference. And then to get to the next term, you add the common difference again. Get to the next term, you add the common difference. So it's just like moving from one term to the next in geometric, multiply by R, multiply by R, multiply by R, add D, add D, add D. And because you're doing that, you generate a very user-friendly formula. And so now we're going to ask the same question that we did with the geometric. Do we get a closed form representation for the partial sum? Is there something that's better than just, okay, I'll just add them up? Is there something better than that? And of course, the answer to the question is yes. So now I'll say we seek a formula for S sub n. And so we can just use the technique we used on the last example. So S sub n, and I think it's neat when you motivate these through very simple examples, it makes the theory seem a lot easier. And sometimes we can do this, not always. It certainly worked that way with the conic sections, didn't it? I mean, we thought about how it would look, even though it was abstract, we drew pictures and motivated everything that way. So we looked at a quasi example, not as specific as this, but it was the same technique that made the understanding of the A and the C come to life, as opposed to just being something completely abstract. So now what we can do is say, all right, here's our general term. So now we'll switch to K. K equals 1 to N. So we have A plus K minus 1 times D. So this is just like the last problem. Let's just break it up into two pieces. So we have K equals 1 to N of A plus K equals 1 to N of K minus 1 times D. Now, again, the first one's easy. We think about this, this is just adding A to itself N times. So that's going to be N times A. That's the easy one. And now, of course, here the D is a constant, so we can factor the D. Just get it out of the way. Now, to make this simpler, you're thinking, well, you can just go ahead and break this up as K, a sum of K, and then a sum of minus 1. But there's an easier way to do this. Notice here, this is adding, in this case, the numbers from 1 to N minus 1, because we start at 0. So we go 0 up to N minus 1. So we don't hit the N. So all we have to do is replace N with N minus 1 in the famous formula, since we stop at N minus 1. So that way we can take easy use of this without any more trouble. So this will give us NA plus, now we'll say N minus 1 times N over 2 times a D. So again, here in the famous formula, replace N with N minus 1. So that gives us a nice formula right there. Now we could stop with this, but you know, that's probably not the best. We want to make it look a little bit better and maybe easier to remember, because this is not easy to remember. So what we're going to do is we're going to think of factoring the N over 2. So we'll do the same here. We'll put in a 2 and pay for it and factor the N over 2 here. So little old trick, multiply and divide by the same number doesn't change anything. Rewriting. So now we can factor N over 2. And what does that leave behind? Well, just 2 times the A plus N minus 1 times D. Now that's a standard formula right there. For the nth partial sum of the arithmetic sequence, this would be considered a bona fide formula. N over 2 times twice the first element, and then plus N minus 1 times the common difference. So again, just like with the geometric, you need to know N, you need to know A, and you need to know D, okay? Well, D is taking the place of R in the geometric. Now, here's one form. Let's go on to another one, and then we'll summarize. We can break this 2A into A plus A. Again, another standard technique. A plus N minus 1 times D. Now, I'll just put brackets around this to kind of give it a highlight. That's just the nth term. That's the nth term right here. So we generate the nth term. So here we have N over 2 times A, the first term, plus the nth term. Now, of course, this turns out to be pretty convenient as long as you can figure out, in this case, the nth term. That means you need to know N. So if that is part of the problem, go for it. Then it just depends on what information is given. The thing is, you need to know n for either, but you have to take the next step, which says, okay, if you know n, give me the nth term, and then use this. So again, that's a personal choice. So now in summary, for the arithmetic, we have n over 2, 2a plus n minus 1 times d, which is this one, or n over 2 times the first term plus the nth term. So that's like n times the average of the first, n times the average of the first and last term, or first and nth term. So this, we get two possibilities here, and you can use either. I like to use this one when I can. I mean, when it just, if it's convenient or whatever, it makes no difference. So again, just remember, the arithmetic doesn't have the calculus rendering. So what you can see here is that this d that we're adding, you know, it's not making the terms decrease in a way. For instance, when you're doing multiplication by r, an absolute value less than 1, it's making the outputs smaller in absolute value, so to speak, so that the outputs are converging to 0. So the idea is that what you're adding to the sum is getting small enough, fast enough, so to speak. You could still add terms that are getting smaller, that is converging to 0, but the rate of convergence may not be quick enough to cause the series to converge, so to speak. So here we're kind of lost. This d is constant, and so it doesn't have the dampening effect on the output. So this would not ever converge in an infinite sense. So there is no infinite sum, partial sum here, just because of the nature of the sequence. But that doesn't mean it's not useful. It's a very useful sequence. It's just not in the infinite case. So that'll make more sense as you get to calculus and understand derivatives about difference quotients and things. That's going to be what you learn in calculus, to understand how things behave in the sense of how things get larger or how things get smaller in a comparison type rate test. So now let's look at an example. So I promised you some examples of these. So the first one we'll do is with arithmetic, then we'll hop back to the geometric. So here's an example. We have a stack of poles. Now, when you go to a lot of the shipyards, you'll see certain objects stacked in a very nice geometric way. Poles are one of these. They're usually in these solid triangular shapes. And so think of it this way, like you see at the shipyard channel, or the shipyards by the shipyard channel, where they basically store everything. For instance, you know, as they take items off of barges and things and organize things, it's this kind of similarity. So for instance, the first layer will have 26 poles. So they'll be arranged in order, juxtaposing each other, 26 poles. And then the second layer will have 25 poles. The third layer will have 24 poles, etc. Now, it says, and there are, in this case, 16 layers. So you're thinking we could just add them up. Well, here's the question. You know what the question is going to be? It says compute the number of poles. So when you look at this, you're thinking this is arithmetic and you can kind of intuit this and get a ballpark figure. But say your boss needs to know exactly. You've got several stacks in the shipyard and they've got different configurations, but they're all arithmetic. So he wants you to figure out, he or she wants you to figure out the number of poles total. So that could be a long calculation when you do all the separate ones. So now what you can see here is these are decreasing by 1. Notice A is 26. That's going to be our first element, so to speak. And then the D will actually be -1 because it's decreasing by 1 each time. -1. And, well, this was a gift. N equals 16. That's how many layers you have. So in this particular case, if we think about the sequence, let's just write down what the sequence is to get as much out of this as we can. This is going to be 26, 25, 24, and then etc. Then at this point, we're thinking, okay, so we have 26 plus, in this case, 16 times a -1. And of course, Professor Ron, that's an n-1. So that's a 15. So let me write the formula up. So for the general, this is A plus n-1 times D. So now, of course, A is 26, n-1 will be 15, and D is -1. So when you look at this is 26 minus 15, which is 11. So we call this A sub 16. Now we're good to go. Sn, I'm going to use the second form, is just n over 2 times A plus A sub n. So equivalently, S sub 16 equals 16 over 2 times 26 plus 11. So that's how simple this is. If you want to go ahead and compute this once you have the n, you might as well do it. It's up to you. It doesn't matter. So this is 8. And then, of course, this gives us a 7 and a 37. So now 8 times 7 is 56 with the 5, 24 plus 5, that's 296. Now, the idea here is that you're thinking, well, I can add this up, I can write it down and then add them up and whatever. But if you have to do several of these types of calculations, and maybe you have an assistant who's gone out and given you all of the characteristics of the stacks, and then you do the computations at your desk. So maybe some of the stacks are quite large. And then it's a little bit difficult to keep up with all the numbers, whereas this organizes everything very nicely. So arithmetic, though it doesn't have the calculus power of the geometric sequence, it certainly is something that occurs in everyday life. So when people will comment about, oh, I don't use mathematics. Well, mathematics is used even when you're not even thinking about it. You think about the technology and the cell phones and everything that are contingent upon computer code, which is contingent upon recursive theory, which is contingent upon mathematics. I mean, there's nothing that we do in our life that doesn't have math in it. And as long as you want to be a STEM professional, the math of Sir Isaac Newton is still important to you. It may not be important to everyone, but for STEM professionals, mathematics is key, and you cannot change that. You cannot change the math that you think you need to learn because we're in a technological era. It has not changed and will never change. And the skills that you learn in calculus will make you better as a STEM professional. It's going to make the difference between having the successful career and the career that you don't necessarily want. And we don't want that. I want my students to do what they want to do, and that's important. Now, let's go back to the geometric. The geometric is kind of interesting in the way that we look at it and say, okay, the arithmetic's not too hard to keep track of, but when we think of geometric, here's an interesting problem from your web assignment. We have 1 minus 1/2, plus 1/4 minus 1/2, 1/8, 1/2, plus ellipsis minus 1 divided by 512. And first, you think about this, well, I guess, Professor Ron, you're asking us to add this. So this is going to be compute the sum. Now, of course, you know, you can use your Google calculator and get a nice approximation, but that's no good. I don't want that. We want exact. We only use the approximation when WebAssign asks for a decimal, but otherwise we want exact. So when we look at this, we think, okay, this is a partial sum, and then we've got a first, let's look at this. We've got a first term of 1, and then we notice to get to the second term, we appear that we've multiplied by -1/2, and then to get to this term, we again multiply by -1/2 to get positive 1/4. So now we see, okay, R is -1/2. So this, just like the arithmetic, we need to compute the n. Now that last problem was really convenient. They said, bam, here's n. You know, here you've got these many layers. So Merry Christmas. You're thinking, okay, well, where's Santa here? Well, we don't see. So we have to do that part. That we're the elves, and so we have to do all the dirty work, and then Santa can take credit for it. Just a little holiday humor, but clearly not very good. Now when we look at this, we're thinking, well, what's the general term? A sub n will just be A times Rn minus 1. So we'll just fill that in. 1, so we get what? -1/2 to the n minus 1. Now, when we start comparing these, notice that we have a negative sign here. So when we look at this, this implies that n minus 1 is odd. So that negative sign survives. So if this were even, it would be absorbed. So we see here that n minus 1 is odd, so that's going to be a little check for us. Now, when we think about this equivalently, we would have -1/2 to the n minus 1 will equal -1 over 512. So when we look at this, the important thing is not so much the sign, but as is the power of 2 that's going to give us this. So if we want to find n, we can reciprocate both sides. This will say 2 to the n minus 1 must equal 512. And we know that n minus 1 will have to be odd. So that's not, again, an issue at all. So in order to go from here to here, we have to solve this equation, devoid of the parity, in this case, the plus or minus. And parity has to do with even and odd. And then, of course, that's intimately related to positive and negative. So we just say, okay, well, let's just do a little bit of symbolic computation. This is just going to be 2 times 256. But we know 256 is a perfect square. That's just 16 times 16. So again, we've got what? 2 to the 4, 2 to the 4. So 2 to the 1 times 2 to the 4 times 2 to the 4 is 2 to the 9. And just like we said, n minus 1 is odd. It's 9. If and only if n minus 1 equals 9, if and only if n equals 10. So the key here is that when we do this analysis, of the general term, we get the actual value of n, which is 10. And so now we can say, let's remind ourselves, S of n is a times 1 minus r to the n divided by 1 minus r. When you take number theory, ladies and gentlemen, the geometric progression is indispensable. That's probably where I used the geometric progression second most as compared to calculus and analysis when I studied number theory. And that's a nifty course in undergraduate as well as graduate. So what we want to do here is say S sub 10, A is 1, so we have 1 minus negative 1/2 to the 10th divided by 1 minus negative 1/2. Now this is exact. Now, a lot of times in WebAssign, you've already found, you start clicking in and you put in the exact expression, you're running out of time, and you think, well, WebAssign is going to scan this to see that it's equivalent to a correct answer. And if it scans this and says, cha-ching, okay, that's fine. Well, for right now, just say we have a client that doesn't want this. They want it a little simpler. And so we want to get paid, so we're going to make it simpler. Touche, that is correct. That is the sum, but let's make it a little bit more user-friendly because we have a little extra time right now. But when you're in a crunch, this will work. Now, if you look at this, you're thinking, okay, well, this is even power, so it'll absorb the negative. So we have 1 minus 1 over 2 to the 10th. And then, of course, minus the minus here, we get what? 3/2. So reciprocate the 3/2, we get 2/3. And now notice we figured out that 2 to the 9th was 5/12. So this implies that 2 to the 10th is just 2 times 5/12. And that's our friend, 1,024. And so we get what? 1 minus 1 over 1,024. So we have 2/3, 1,024. So 1,024 minus 1. So we have 2/3. So that's going to give us what? 1,023 and 1,024. Well, we know that's just, we went forwards to go backwards. So that's going to be 5/12 when we divide by 2. And then, of course, 2 plus 3 plus 1 is divisible by 3. So this is divisible by 3. So that's going to be what? A 3 and then a 12. So that's a 4 and then a 1. And of course, that's just powers of 2. So that's reduced. So our client will be happier when they see this. Okay, so this sum here is actually 341 divided by 5/12. So the thing is that my grandfather on my mother's side used to tell me of someone he knew that was an accountant and that they could add numbers like a computer. They could just run their finger down a string of numbers and boom, to tell you the sum to the perfectly. Okay, that is a gift of arithmetic. And so that's what Srisvana Ramanujan had. He was the Indian mathematician genius whose work paralleled that of Sir Isaac Newton. And so when I was younger and working math, I was good with numbers, but I was more adept at doing theoretical aspects. I would take problems and I would dissect them and work out the algebra and the geometry. And it was always weird because I didn't know why I liked to do it. I just did it. My mom would put these little numbers from the newspaper, little problems, stick them on the refrigerator, and I'd take it down and work them. And this is what reminds me of these kinds of problems, because you may think that you have a ballpark figure. Now, Ramanujan could look at this and boom, he could get it. Amazing. So what Professor Ron would do would analyze the mathematical theory and go about it a different way. And so that's what we're learning here. So if we can't be Ramanujan, we can be the next best thing. So it's unfortunate that Ramanujan became ill with pneumonia as he was trying to adapt to the cold weather in England. No telling what he would have done. I don't know that it would have surpassed the genius that he left us, but kind of like Mozart, no telling what would have been composed had they lived to be, 60 or 70. It's amazing. Okay, now, so think about that. Think about Ramanujan when you're doing these to give you that leg up, so to speak. Now, what other impact will the geometric have on the calculus? When I teach the kids in calculus 2, they use geometric all the time. So here's something that you're going to see a lot. For instance, let's consider x in absolute value less than 1. And look at this sequence. So in the infinite case, if this were R, if x were R, this would be convergent. So we could look at 1, x squared, x cubed, x to the 4th, that, and then x to the n minus 1. So that's the first term, the second term, on down to the nth term, etc. So this would imply that S infinity would be the sum. Let's just go ahead and use n since we don't have a n up here anymore. N equals 1 to infinity. And this would be 1. Well, a is 1, so note a equals 1, r equals x. Okay, so let me touch up. There we go. Hold on, if I click outside the box, the IPEVO goes away. I've learned my lesson, but you would think I wouldn't even hesitate. So now we get x to the n minus 1. Now, if you like, you can re-index. You can replace n with n plus 1, and so make this smaller by 1. So we can also re-index n equals 0 to infinity x to the n. So here, replace n, we've done this before with the k, replace n with n plus 1. And so if we do that here, we have to make this smaller by 1. Increase, decrease, balance it out. But now, of course, we have the formula a, which is 1 over 1 minus r. So this series here converges to that. That is a remarkable formula that you will use widely in calculus 2. It is indispensable for the theoretical progression of power series. Amazing, just like the Pythagorean theorem. So the beauty of this theorem means that you can recast inverse trig functions, anything that has this form. I mean, there are all kinds of applications that you can use here that you can't even think about. And then you can also add in the concept of partial fraction decomposition to expand it. So this geometric progression, big time important. So when you see it again, you can relish the fact that you had some time to spend with it in this class, and that it won't just be like somebody throwing cold water in your face. I've never seen this before. You will have knowledge of this, and that's what will make the calculus a little bit more doable. So now I wanted to say a little bit about parity and more about telescoping, and then another example of the geometric. So let's consider this example. I had a student working on this in the infinite case yesterday during my conference hours, and I thought, well, let me just recast this for a pre-calculus problem. So we have 1 plus -1 to the ith power. So in this case, yesterday we had I equals 0 to infinity. And the student was worried about how they would write this in the WebAssign. And I said, well, you know, that would be okay for WebAssign leaving it alone. But if you want to neaten it up, I showed him how to do it. And I thought this would be a great pre-calculus problem. Now, when you look at this, you're thinking this is a nice finite sum, so we can just go ahead and break it up into two pieces. Notice the sign's going to alternate here. So we get I equals 1 to 50 of 1 plus, now we have I equals 1 to 50 of negative 1 to the I. Now, what I wanted to note here is that when you have this negative 1, this is what we call alternating. So for instance, we would say, if we had something over here like I negative 1 to the I, we would say, what does this equal? Well, this is negative 1 when I has odd parity. I is odd, like 1, 3, 5, things like that. And positive 1 when I is even, a multiple of 2. So when we do the trigonometry, we know that 2k plus 1 is odd when k is an integer, and 2k is even. We use that all the time in trigonometry. For instance, you know, pi k, looking for zeros of sine, odd multiples of pi over 2 are zeros of cosine when we're on the axes. So this is a common occurrence in the trigonometry. We did a lot with even and odd there. But now we're focused on the sign as opposed to the parity here. And so when we do that, we're thinking, okay, well, let's see, is this actually telescoping? Let's check. Let's use this and see if this is actually telescoping. Now, this is just adding 1 to itself 50 times. That's easy. That's just 50 times 1. And now here, let's write out some terms. Notice when I is equal to 1, we just get negative 1 to the 1, which is negative 1. And when I is equal to 2, we get negative 1 to the 2. So that is positive 1. So if we start with 1 and 2, so we can say k equal 1, 2, and then k equals 3, 4, we get the same thing. And we keep going all the way to k equals 49, comma 50. Now, depending on the parity of that number will change the answer. But this is also negative 1 plus 1. And this is telescoping. All of these terms are 0. So when you do this problem, you just get 50. So the idea is that in the infinite case, we have to do a little bit different analysis. It's the same as this, but when you consider the fact that we can break up convergent sums into pieces and analyze them separately, we get a very interesting result. This is, again, telescoping. All of these absorb, 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 absorb. Now, of course, if we had a 51 up here, the answer would be negative 1, because that would be the only term that wouldn't get absorbed. That'd be a negative 1 straggling right out here, and we get 49. So the thing is that when you've got these finite sums, you really do have to look at what you've got up here as an even or odd number. So the telescoping impact is very evident here. And again, just like geometric is very simplifying in many ways, just like arithmetic. Now, of course, this would never converge because it can't decide what it's doing. I mean, it's negative 1, then it's positive 1. It's negative 1, then it's positive 1. Sometimes you get 0. Sometimes you get negative 1. I mean, this cannot settle down. It doesn't mean that the function is becoming infinite. It just means that it's never going to have limit 0 because it can't decide. It's just going to hop around. So that's going to be a term that you use in calculus called diverges by oscillation, just like trig functions do. So that'll be something you'll see more of. So I thought that would be kind of a fun problem. Now, let's look at another example of the telescoping. Like the arithmetic and the geometric, I want you to know about these. And let's look at this particular generating sequence. Say we have 5 times the, now remember when we have log, that means base 10 logarithm. So we have log of n divided by n plus 1. So that's our general term. Now what we could say here, in this particular case, like n is greater than or equal to 1, right here. So now when we look at this, we're thinking, okay, well, if we look at this and say, what's going on here? Well, we can use a logarithm identity. This would just be 5 times the log of n minus the log of n plus 1. That's the identity for the log of a difference. And then you look at that and say, oh, wait a minute, Professor Ron, that's going to telescope when we do the partial sum. Because again, notice this will eventually become n plus 1, which will absorb that. And as we'll just kind of trail off, because notice the difference between the arguments is 1. And this minus sign means that we're going to get absorption of terms, but the extremes will survive, possibly. So let's just write this down. So we're going to say, what is the nth partial sum? Now you can do all kinds of partial sums here, but what's nice about this, when you use the equivalent expression for the general term with the log identity, you transform what this partial sum is going to be, and you open the floodgate, so to speak, to the intuition that will now follow. So now this implies that S of n will just be the sum k equal 1 to n 5 log of k minus log of k plus 1. Oh, I don't need all these. Let me use I didn't use a bracket on the other end. I'll just use another parenthesis. Okay. Now, of course, the 5 will factor. So we have 5, k equals 1 to n log of k minus log of k plus 1. Now, let's just write out a few terms, because you see they're gonna telescope. So we get 5. So we have k equal 1 log of 1 minus log of 2. And then we have plus. Now this is k equal 1, now k equal 2. So log of 2 minus log of 3. So it's going to telescope. You see, these are just going to absorb, because these arguments are only separated by 1, or even 2, we'd still get absorbed, and we just have more surviving terms. And plus log of, in this case, 3 minus log of 4, etc. So let's put on some more terms. So we'll have log of, let's see here, we'll do n minus 1 minus log of n and then the very last term, when we get k is equal to n, we get log of n minus log of n plus 1. Now notice, this term survives because it can never be absorbed by any of these others. It's 0 anyway, but it still survives in the sense that it didn't get absorbed by another term. Absorb, 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 absorbed by the previous. But none of these will ever have this argument. Survives. So when it comes to telescoping, telescoping sums are very useful. The thing is that pretty much all of the terms go away, and we're just left with the stragglers, so to speak. So now we say, okay, well, we just get 5 times the natural log, or the base 10 log, common log of 1, minus the common log of n plus 1. but that's 0, so we just get -5 times log of n plus 1. That's it. So lots of times when I tell my Calculus 2 students, I said, don't look at these and fail to use the logarithm identities, because that's opening the door to a telescoping sum. And you will see this with partial fraction decomposition when you start studying series in your Calculus 2 class. It's very important to recognize patterns. And so now you could say, well, what's S of 23? Now you, like a magician, you have -5 natural log of 24. And you're done. Because now you have a closed form representation of S sub n right here. So when you've got a special type of sequence, you get nice simplification. And in mathematics, we like to take advantage of that because that makes our life easier. You see, this simplification here due to the telescoping effect, telescoping. Folks, when you get to calculus and you're doing this and you're going to think back to how hard I worked you in this class, you're going to be thankful. You'll be like the students that say, well, Professor Ron, you were so hard on us. But when I took calculus, it was easy. I actually understood it. The reason being is that I have designed classes in calculus sequence for non-honors and honors, and it's all the same. You have to have a foundation. And with that foundation, everything will make sense. Everything will be crystal clear. I mean, you can spend time learning the calculus instead of spending time on the items that you should already know. You can't appreciate a course. We've all been there, ladies and gentlemen. We've all been in a course where we thought, I should have worked harder in this previous course. And then you're like, oh man, I got to review. That's not a very, very fun experience because you're just like living from day to day. We don't want that. We don't want that for our education. We want to be prepared. I mean, it's hard enough when you are prepared. So this is why I try to focus on the things that you will see again. And this is a very important concept. Just to see it now will make it easier the next time you see it. And then you'll smile and say, oh, that telescopes. Now, there's another example that I found in the WebAssign. I'm always looking for new problems that I think you can enjoy. And here's one. And then I'll do a quick one with the geometric. For instance, we'll say write this number, 0.777, etc., which is 0.7 repeating as a fraction. As a fraction. Now the thing is that you know this is a repeating decimal. Repeating decimals are represented by fractions, okay? Non-repeating, you know those are irrational because if they had a repeating decimal, they wouldn't be irrational. It's just a vicious cycle, right? So you're thinking, let's just mask this as a geometric progression. So now we say 0.7, let's just write it down. This will be 7 over 10, that's the 0.7 part, plus 7 over 10 times 1 over 10. So this is the 0.7, this is the 0.07. That just moves us over 1 decimal. Now, how do we get that third one? We just say 7 over 10 times 1/10 squared. This gives us 0.007. And then how do we get the next one? Well, let's just keep going. 7 over 10, 1/10 cubed. That gives us 0.0007, etc. So when you have a larger repeating unit, this number will be bigger because you're going to shift down depending on how big the unit is. If it's 2 units, then it's going to be 1 over 100 to shift to the next unit. If it's 3 in the unit, it'll be 1 over 1,000. So it's not hard to make the adjustments to whatever the repeating part is. So now what we see is that 0.7 repeating is just a what? Infinite sum. Well, what is it? Well, this is like the 1 over 1 minus x bit, but a little bit different. So notice A is 7 over 10, and R is also, well, almost 7 over 10. It's 1 over 10. So we have written this as a geometric progression or as a infinite sum. So now n is no longer in the picture. It went off to infinity. So we have S infinity equals 0.7 repeating. So this will be 7/10 divided by 1 minus 1/10. A divided by 1 minus R. So this is 7/10. And of course, this will be a 10 minus a 1. So this is 9/10. The 10's absorbed, and we get 7 over 9. So that's not a surprise to you at all. 0.7 repeating is actually 7 over 9. And you can practice with this. You can make up your own problems. Now, the idea here is this is an excellent example of what it means for a particular number to have geometric properties in the sense of a geometric progression. And you probably talked about this in a previous class. This often comes up at Math Club, or it comes up in Algebra 2 or something. It's something that you can do in other ways. But this makes an excellent application of the geometric sequence. Now, the last problem I want to do, again, the geometric is a little bit harder than the arithmetic, but that's okay. Arithmetic is easy to set up. But I wanted to do enough with that so you understood it, but I wanted to spend a lot of time on the telescoping and geometric and a lot of the algebra that is involved with these, so you will be able to kind of build to the next level. Now, this particular example says a ball is dropped. A ball is dropped from a height of 8 feet. From a height of 8 feet. This is really a physics problem. Then it bounces up, so we can make a nice model out of this. One third of the distance it has fallen. Then it says find the total distance the ball has traveled at the instant it strikes the ground the 5th time. Now, this can be generalized, and in the Webassound problem, you can take the answer we have here and generalize it for whatever time here, maybe the 6th time, the 10th time, or 20th time. You don't have to completely rework the problem. It can be generalized. But this is a nice example. Now, the thing is that you think of a height. We know that the path is parabolic, and we get some kind of a cycloid bit. So it's like you drop, and then you hit once, then you hit again. So there's the first, the second, the third, the fourth, and then the 5th time. So here's the first strike, the second strike, the third strike, the 4th strike, and the 5th strike. So the neat thing about this problem is that this little model helps you to organize your thoughts. Otherwise, it's easy to leave something out. So when it bounces, you get a twofer. It goes up and then comes back down. So we have to think about it this way. And then by the fifth time, the distance traveled is just adding all of these, and we've got a twofer here that we don't have over here. So now we can use the hypothesis to write the numbers down, and then maybe notice that we do have maybe possibly something geometric, and get an actual number that we can put in together. As you know, like the client says, okay, I don't want a string of numbers, give me one number. So let's see if we can do that. So distance traveled, so we start out with 8, and now we get the twofers. So notice here, this will be 1/3 of the distance that it fell previously, but up and down. So 2 times 8 times 1/3. Now we're going to go 1/3 of the distance that it fell here. So 1/3 of this. So we got up and down 2, 8 times 1/3 squared. So check, check. Now let's do it again. Up and down, and now 8 times 1/3 cubed. So this is geometric, check. And then the very last time here, up and down, 8, 1/3 to the 4th. So each time we take 1/3 of the distance it fell previously. So we're always doing the 8 times 1/3, no, 8/3 times 1/3, etc. So now you're thinking, okay, what part is like geometric? Well, we've got some riffraff out here. We don't care about that. We don't forget the 8, but it's not part of the geometric progression. So we have 8, and then notice, this is a nifty little problem. So we've got this common factor here in all of these. So we've got a 16, and then we have this geometric progression, 1/3. Now we can just write it out. 1/9 plus, well, let me just do it this way. Let me just keep it in the form with the thirds, so it's real clear that we got geometric. That way it looks better. I'll just leave it like this. Now this is geometric. So we have this point over here, A equals 1/3, R equals 1/3. Seen this one before. I promise I wasn't thinking about this when I did that first problem, but how fortuitous, right? And N equals 4. We got 4 terms. We got A is 1/3, R is 1/3. So now let's fill it in. So this is 8 plus 16. So now we have 1/3 times 1 minus 1/3 to the 4th divided by 1 minus 1/3. So we have 8. So we have plus 16. So here we've got a 1/3. So we do 1/3. And then, of course, this is a 1 minus a 1/3, which is a 2/3. So the 3's are going to absorb. And then we have 1 minus 1 over 81. So now the 3's absorb. So we get 8 plus 16 divided by 2. The 2 survives. And we have 81 minus 1 over 81. So this is an 8. And of course, the 2 into the 16 is an 8. And we're left with 80 over 81. And let's see here. Now, if we look at this, and you're thinking, at this point, is this good enough? Well, let's just say our client wants a fraction. So now we can get a common denominator. So we have 81, and that'll be what? 8 times 81 plus Of course, that's 8 times 80. So actually, it's easier just to add them up without factoring it, because then I've got, that's going to be a what, a 161. So let's do this. This will be what, 64 with an 8 plus 640, right? And so that'll be what, 8, and then we've got an 8, and then a 12. So 1,288 divided by 81. And that's how far the ball has traveled in feet. So when you look at this problem, it seems very simple. Oh, just 1/3, and times another 1/3 times another 1/3. But the little kink is that it's bouncing. And so you have the up and the down. And so it's easy to forget that with the up and the down, you get the factor of 2 in all of these cases. And then, of course, this is kind of riffraff here. This is the geometric part. And so what the WebAssign will ask you to do is take this formula here and generalize it to any number of strikes, which you can easily do by the way I've set this up here. So what I wanted you to see today is that sequences have always been a part of your life. They're just functions. You've been dealing with sequences. But the key with the sequences is that you can always come up with a general term formula as long as it does what you need it to do. It's not necessarily unique. Very rarely is it unique unless we have a convention like we have with the telescoping or the geometric or the arithmetic. So we have a sequence. From the sequence, we generate a sum, the partial sum. The partial sum itself is a sequence. And so we investigate the partial sums. So when it comes to dealing with sequences, you've got the generating sequence, and then you have the partial sum, which is also a sequence. So when you do infinite series, you investigate sequences of partial sums, because that's what an infinite series is. You start adding up first term, the first 2 terms, the first 3 terms, the first 4 terms, the first n terms, and then you see if that sequence has a limit. That's what an infinite series is. Hopefully when you get to calculus, you'll remember that. I've had untold students who don't know me to come by my office and say, Professor Ron, what's an infinite series? And I'll say, well, it's a sequence of partial sums. Well, do you have a moment? Can you flesh that out for me? So what I want you all to do once you finish your test is then spend some time on this when you have a little bit of time to rest. And then next week, we'll cover mathematical induction and the binomial theorem and kind of pull everything together. So I wish you well. I'm glad that you all were able to make it today, those few that could. And I wish you well with your testing. Use tomorrow if you need that flexibility. And then please take care of yourself. Like I say, the COVID is we're getting to a point to where things are improving with the vaccines, but the main thing is just to take care of yourself, wear that mask, and be safe. So I appreciate your time today. You all have a great day, and also enjoy the little bit of time that you'll have off, and we'll see you when you get back. Bye, everyone.